In this video, we're going to talk about graphing polynomial functions. So we already know what y equals x looks like. That's a polynomial function. It looks like a line. That's x to the first power. We don't write the first power if we just have x to the first power. We just leave it as x. If I have y is equal to x squared, I know that's a polynomial. That looks like a parabola. In this video, we're going to talk about what it looks like when we have higher degrees, like x cubed, or y equals x to the fourth power, or y equals x to the fifth power. We're going to talk about what those look like. But before we talk about what those look like, we have to talk about, or remind ourselves, how we can go between standard form and factored form, because that's really important for graphing these higher degree polynomials. So if I have factored form, I need to be able to convert to standard form. All I'm going to do that is FOIL. That's all I'm going to do. So I'm going to multiply the first two parentheses together here for this problem, and then I'll multiply the last factor. So I multiply everything in the left parentheses by everything in the middle parentheses. X times x is x squared. X times 3 is 3x. I have negative 1 times x, which is negative x, and negative 1 times 3, which is negative 3. Then I'm multiplying this by that other factor, x minus 4. I'm going to clean this up to be x squared plus 2x minus 3 times x minus 4. All right, now I have three terms multiplied by two terms. I want to make sure I don't forget anything. This is a lot of terms to be multiplying together. So I'm going to make the area box, and I'm going to make it 3 by 2. I'm going to have x squared plus 2x minus 3 as one side length, and x minus 4 as the other side length. And I'm going to multiply everything together, and this way I don't forget anything. So I have x times x squared is x cubed, x times 2x is 2x squared, x times negative 3 is negative 3x, then I have negative 4 times x squared is negative 4x squared, negative 4 times 2x is negative 8x, and negative 4 times negative 3 is positive 12. And then I like to start with, I'm going to add all of these things together and combine my like terms. I like to start with the highest power, which is x cubed in this case. And then I have two x squared terms added together. Negative 4x squared plus negative 2x squared is negative 2x squared. Then I add my x terms together. Negative 8x plus negative 3x, which gives me negative 11x. And then I have that constant plus 12. This is the standard form of that factored form that was given to me. All right, I want you to pause this video and try this example on your own. What you should have gotten for this example, at this point, x plus 3 squared, we've done it so many times to complete the square. You should know it's x squared plus 6x plus 9. And I'm multiplying that by x plus 1. Now I have 3 terms multiplied by 2 terms. That's a lot of terms to multiply together, so I'm going to make the area box. And I'm going to have one side length, x squared, 6x plus 9, and then the other side length is x plus 1. Multiply all of this together, I get x cubed, 6x squared, 9x. 1 times all of this stuff is just all of that stuff. So x squared, 6x, 9. And then I add everything together. Starting with my highest power, I have x cubed. I have 7x squareds. I have 6x plus 9x gives me 15x. And then I have that constant 9 at the end. And this is the standard form of that factored form. I also need to be able to go from standard form to factored form. So this is standard form here. I need to be able to factor that thing. First thing I check when factoring is I check the GCF. So I'm going to check if these terms have anything in common. And looking at their coefficients, I can see they all have 3 in common. Looking at their variables, I can see they all have an x in common. So I know the GCF of these 3 terms is 3x. I'm going to take that out and rewrite this as 3x times, I know 3x times x squared gives me 3x cubed. I know 3x times negative 6x gives me negative 18x squared. And then I know I have 3x times 8 gives me 24x. From here, looking at this thing, I know that's in the form ax squared plus bx plus c. And I can think of 2 numbers that multiply to 8 and add up to negative 6 using the diamond. So this thing is factorable. I need 2 things that multiply to 8 and add up to negative 6, and those 2 numbers are negative 4 and negative 2. So I know that this thing, since a is equal to 1, goes straight to factored form using these 2 numbers x minus 4 times x minus 2. And I have this 3x I can't forget about that I took out. I have to include that in my factored form. This is the factored form of that standard form that was given to me. All right, I want you to pause the video and try this example on your own. In this example, I have 2x cubed plus 10x squared plus 12x. I'm taking out the GCF, which is 2x. And I'm going to rewrite this as 2x times x squared plus 5x plus 6. I'm going to look for two numbers that multiply to 6 and add up to 5. And those two numbers are 3 and 2. So this quadratic expression, since a is equal to 1, breaks down immediately into x plus 3 times x plus 2. And I can't forget about this 2x that I took out. So I need to include it in my factored form. This is the factored form of the standard form that was given to me. The thing that determines the shape of a polynomial is the highest power in the polynomial. It's the highest power because, well, the highest power has the most power. When I look at exponential growth, so if I compare x squared to x cubed, and then I compare x cubed to x to the 4th power, x to the 4th power is so much bigger than x cubed than x to the 3rd power is to x squared. Powers, and x cubed is so much bigger than x squared, and x to the 4th power is so much bigger than x cubed. They hold so much more value and power that they are going to control the polynomial. They're going to take shape of that higher power. So I'm concerned when I'm looking at polynomials, especially what's the highest power? What's the degree of the equation? What's the highest power in a polynomial? That's going to determine the shape. So I want to look at a bunch of equations of polynomials and their graphs. So we're going to start by looking at these 3 graphs here and their equations. I want you to pause this video and think about, what do all of the above equations have in common? So what do all of these equations have in common? What you should have noticed is that all of these equations, because we've been working with these quadratic equations for so long, all of these equations have an x squared in common. They all have x squared. If I FOIL this thing, I'm going to get 2x squared. They all have x squared in common. And that's important. That's the highest power. Also, in all of those equations, x squared is the highest power. So, highest power is x squared. Another thing that's really important when I'm looking for the shape of a polynomial, these all have the same shape, and the reason why they all have the same shape, I mean, the highest degree in all of these equations is x squared too. What makes these equations different, so A, B, and C, different from D, E, and F? They all have x squared as their highest power. The difference is the coefficient of that highest power. So the coefficient for A, B, and C for those x squareds is positive. I have a positive coefficient for that highest power, x squared. So I have 2 here, I have 1 here, positive 1 here. They're all positive. For if I look at D, E, and F, like I said, what they have in common is the highest power is x squared. So I can see I have x squared in all of these. If I multiply these two together, I know I have x squared is my highest power. And the difference between D, E, and F and A, B, and C is that the coefficient is negative for all of these. I have a negative coefficient. This will be negative x squared when I FOIL. So negative coefficient for x squared. I want to know, what do all of the above graphs have in common? So I've decided what's important to take out of the equation. Now, what's important when I'm looking at the graph? So we know that the difference between these graphs and these graphs is these, when I have a positive coefficient for my highest power, I'm going to have an upwards parabola. When I have a negative, I'm going to have a downwards parabola. And what's important to note is the end behavior. So what's happening as I go to the left? Oops. What happens as I go to the left? And what happens as I go to the right? So that's what the end behavior is. So what happens as I go to the left in these three? As I go to the left, I'm going upwards. What happens as I go to the right? I'm also going upwards as I go to the right. So what I notice about these graphs is that they have the same end behavior. So same end behavior to the left and right. And to the left, just to clarify, to the left I'm going upwards, and to the right I'm going upwards. So both upwards in both directions. When I look at these three graphs, I can see that as I go to the left here, I'm going downwards. As I go to the left here, I'm going downwards. As I go to the left here, I'm going downwards. And if I look what's happening when I go to the right, I'm going downwards. To the right, I'm going downwards. To the right, I'm going downwards. So I, again, have the same end behavior to the left and right. But in this case, to the left, I'm going downwards. And to the right, I'm going downwards. So the difference between these three is I'm going upwards and upwards here, and I'm going downwards and downwards here. All right. So I can deduce that if I have an equation with the highest power x squared and a positive coefficient, the end behavior is going to look like this. As I go to the left, I'm going upwards. As I go to the right, I'm going upwards. If I have an equation with highest power x squared and a negative coefficient, the end behavior is going to look like this. So I'm going, as I go to the left, I'm going downwards. As I go to the right, I'm going downwards. All right. So all of those equations are, we call them second degree equations. The degree of an equation, the way I name an equation, is based on its highest degree, and these are second degree equations. Now we're going to look at, now we're going to move on to these graphs here. So I'm going to compare them. If I look at all of these equations, I want to look for what do they have in common. Or I want to look at all of these equations. What do they all have in common? Every single one of them has their highest power is x cubed. If I were to FOIL A, I see I have x minus 1 times x plus 1 times x plus 1. If I FOILed this thing all the way out, I know my highest power is going to be x cubed. So the highest power is going to be x cubed. Positive 1x cubed. If I multiply all my first terms together, that's what I'm going to get. Here I have x cubed is my highest power. Here x cubed is my highest power. Same thing in D. If I multiply those all together, I'm going to get negative x cubed is my highest power and sign. Here I have x cubed. Here I have x cubed. All right, so all of them, what do all of the equations have in common? Their highest power is x cubed, and that goes for both sides. So highest power is x to the third power. What's important about the ones on the left that makes them different from the ones on the right is that their coefficient is positive. So I have positive 4 in front of I should highlight this instead. I have positive 4x cubed. I have positive 2x cubed. And here I'm going to have positive 1. So positive 1x cubed. They all have they all have a positive coefficient. So positive coefficient for x cubed. These all have a negative coefficient. So a negative coefficient for their x cubed terms, their highest power. So negative coefficient for x cubed. And as you can see, their graphs look different. These three graphs look different than these three graphs. And the reason why is because of that positive and that negative in front of the highest power. I also want to talk about what do all of these graphs have in common? What do they all have in common with each other? And what they all have in common with each other is their end behavior. So as I go to the left, I'm going downwards. As I go up to the right, to positive infinity, I'm going upwards. As I go to negative infinity for x, I'm going downwards. As I go to positive infinity for x, I'm going upwards. Downwards to the left, upwards to the right. So in this case, I have the end behavior is different on each side. So different end behavior on both sides. To the left, I'm going downwards. And to the right, I'm going upwards. If I look at the other three, if I look at these three graphs and compare them, I can see they are also going in different directions on each end. Different directions on each end. To the left, I'm going upwards. To the right, I'm going downwards. So the difference is that, they're different end behavior on both sides. But as I go to the left, I'm going upwards. And as I go to the right, I'm going downwards. So, what I can deduce from this, if I have an equation with the highest power x cubed and a positive coefficient, the end behavior is going to look like this. I'm going to be going downwards to the left and upwards to the right. If I have the highest power is x cubed and I have a negative coefficient, the end behavior is going to look like this. So I'm going to be going upwards to the left and downwards to the right. All right, let's look at, those are all third degree equations. Let's look at these equations. So all of these equations here, what do they all have in common? All those equations have that their highest power is x to the fourth power. If I multiply all of these factors together, I have 4 different factors there. So my highest degree will be x to the fourth power. For here, I have 4 factors there, 4 expressions with x in them that I'm multiplying together, except I have this negative in front, so my highest power is negative x to the fourth power there. But all the other ones you can very obviously see, x to the fourth power is the highest power in all of them. All right, what do all of these have in common? Highest power is x to the fourth power. I wonder if I can copy this and paste. Yes, I can. And paste. So highest power is x to the fourth power. The difference between these three on the left here, A, B, and C, from D, E, and F, is, again, the coefficient, the sign of the coefficient for that highest power. So positive coefficient for x to the fourth power, and this one has negative coefficient for x to the fourth power. When I look at these graphs, I'm concerned about their end behavior. So they don't all look exactly the same for x to the fourth power. This one has a weird funky thing going on in the middle. This one does not. This one looks a little weird. Looks a little different. It's not symmetrical. But what they all do have in common on for these three graphs here is that as I go to the left, I'm going upwards. As I go to the right, I'm going upwards. As I go to the left, I'm going upwards. As I go to the right, I'm going upwards. As I go to the left, I'm going upwards. As I go to the right, I'm going upwards. So, same end behavior to the left and right. And that is upwards. And then for these, the end behavior is the same on both sides, but I am going downwards as I go to the left, downwards as I go to the right, even though the shapes don't look exactly the same. So same end behavior to the left and right, but I'm going downwards instead. So if I have an equation with the highest power, x to the fourth power, and a positive coefficient, the end behavior is going to look like this. It's going to look like this. So I'm going upwards as I go to the left, upwards as I go to the right. If I have the highest power, x to the fourth power, and I have a negative coefficient for that x to the fourth power, I know that my end behavior is going to be downwards as I go to the left and downwards as I go to the right. So it's going to take, the ends are going to look like that, even if the middle doesn't. All right, and all of those are fourth degree equations. Fourth degree equations. All right, now for these, if you didn't notice the pattern, these are all fifth degree. These are all fifth degree equations. And these also are not exactly the same shape. But as I look at these equations, I know highest power is x to the fifth power for both the right side and the left. Sorry, the left side and the right side. Come on, paste. Paste. All right, so the highest power is x to the fifth power. I also know, or the difference between A, B, and C and D, E, and F, those equations are, again, the same exact thing as we were saying before. I have a positive coefficient and negative coefficient. As I look at the end behavior, for the end behavior for A, B, and C, as I go to the left, I'm going down. As I go to the right, I'm going up. As I go to the left, I'm going down. As I go to the right, I'm going up. Left down, right up. So left, it's different on both sides. So let me say that. Different end behavior. Left down, right up. Again, here, different end behavior. Left up, right down. Left up, right down. Left up, right down. So different end behavior on both sides. So I should say on both sides so you don't get confused. And as I go to the left, I'm going up. And as I go to the right, I'm going down. So, down. So if I have the highest power is x to the fifth power and a positive coefficient, it's going to look like this. Oops. As I go to the left, I'm going down. As I go to the right, I'm going up. And if I have x to the fifth power and a negative coefficient, I know the graph is going to look like this. I'm going as I go to the left, I'm going up. As I go to the right, I'm going down. So let's summarize all of that. When I have y is equal to x squared and a positive coefficient, I'm going to have end behavior that looks like this. If I have x cubed, my end behavior looks like this. If I have x to the 4th power, my end behavior looks like this. If I have x to the 5th power, my end behavior looks like this. I can see very easily that y equals x squared is the same as y equals x to the 4th, if I'm talking about the end behavior. And y equals x cubed is the same as y is equal to x to the 5th power. Then if I look at if I have a negative coefficient, so y is equal to negative x squared, that end behavior looks like this. Y is equal to negative x cubed, that end behavior looks like this. If I have y is equal to negative x to the 4th, that end behavior looks like this. And then if I have y is equal to negative x to the 5th, that end behavior looks like this. So what do I notice about all of these? Well, I also notice that negative x squared and negative x to the 4th are the same. And negative x cubed and negative x to the 5th power are the same. So I want to know, what pattern do we see for the difference between a positive and negative coefficient equation of the same degree? So when I'm looking at these two equations, what do I notice? When I'm looking at these two equations, what do I notice? These two. And these two. They are all opposite end behavior. Which makes sense because they flip upside down when I have that negative. And that's true for all functions. So opposite end behavior. This one was an upwards parabola. This is a downwards parabola. This is not a shape. It's an S, but can't really describe it as an S. But they're opposites of each other. Right? Okay. And then what pattern do we see for even degree equations? When we have even degree equations, it's different for if I have a negative coefficient or not. So if I have a positive coefficient, it's going to be, the shape looks like this. And if I have a negative coefficient, so if I have a negative coefficient for the even powers, the shape looks like this. And then for what pattern we see for the odd degree equations, if I have a positive coefficient, they look the same. So positive coefficient looks like this. And a negative coefficient, spelled that wrong. Oh my gosh, that's so wrong. Whatever, that says coefficient. And then that shape looks like this. All right, so let's talk about, for the graph to the right, we're going to identify the important information from it. So if I look for the relative relative maximum, that is right here. That's point A. If I look for the relative minimum, I'm looking at this point here. That's the lowest point. If I'm not talking about how it goes on in its end behavior to infinity. So relative minimum is this point B. The x-intercepts are -1, 0, 0, 0, and 1, 0. So -1, 0, 0, 0, and 1, 0. This is the important information that I need to talk about when I'm graphing polynomials. So I also need to know the y-intercept. The y-intercept in this case is the same as the x-intercept, 0, 0. So I'm going to say 0, 0. These are the important points that I can pick from the graph and that I'm going to use to graph polynomials of higher degrees. Another important thing to notice is when I have a multiple 0. So a multiple 0 in an equation in factored form is a 0 that appears, so multiple times, more than one time in factored form. And when I have a multiple 0, or if I have a multiple 0, I want to talk about the multiplicity. So the multiplicity is how many times that 0 appears in factored form. And if that multiplicity is even, this is the important part, if it's even, then that means the graph changes directions at that x-intercept. So if even, graph changes direction at that 0 or that x-intercept. Okay? All right, so let's try to use everything we just talked about to graph this thing here, example 1. So let's try to use all that information and all that important information that we just talked about, including the end behavior. So I have in factored form, and that's what I need in order to graph, y is equal to x plus 1 times x plus 1 times x minus 4. So what I want to do first is talk about what is my end behavior. So what's the end behavior going to look like? Oops. What's the end behavior going to look like? And I know I have, if I foiled all of this, and that's why it's important for me to convert from factored form to standard form, I would see I have y is x cubed. X cubed is the highest power, and that's what's going to concern me, or that's what I'm going to use to find the end behavior. I know if I have y is x cubed, and that's going to have a positive coefficient, my end behavior is going to look like this. So I'll be going downwards as I go to the left to negative infinity. I'll be going upwards as I go to the right. So that's the end behavior, important. Then I'm looking for the important points. I'm looking for the x-intercepts to start, because those are easy to find when I'm given factored form. And I can just look at the factored form to find. I know it's when x plus 1 is equal to 0. When x plus 1 is equal to 0. Oh, those are the same. X minus 4 is equal to 0. So I have x-intercepts here. One is negative 1 comma 0. The other one is negative 1 comma 0. So I'm seeing the same thing twice, which means I have a multiplicity here. This is a multiple 0. So this is a multiple 0, negative 1 comma 0. Multiple 0. And it has a multiplicity of 2. It shows up 2 times. So because that's an even number, which is even, I know the graph is going to change direction at this point. So graph will change direction. Okay. And then the last important thing I'm going to take from my equation is the y-intercept. So the y-intercept I know is when I plug in 0 for x. So I have y is equal to 0 plus 1 times 0 plus 1 times 0 minus 4. And that gives me y is equal to, I can just multiply the constants in my factored form. So 1 times 1 times negative 4, which gives me negative 4. So y is equal to negative 4. That is my y-intercept. So these are the important points that I'm going to plot. On the graph, I have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and I have 0, negative 4. That's my y-intercepts. I have negative 1 comma 0. That shows up twice. And then 4 comma 0. Okay. And what I'm going to do here to start, I'm going to use the end behavior to start. I know that as I go to the left and plug in higher and higher, bigger and bigger negatives, I'm going to get bigger and bigger negatives if I plug that in for my highest power, x cubed. So I'm going downwards to the left, and that's what I see in my end behavior here. As I go to the right from my endpoint here, I'm going to be going upwards. So I should be going in 2 different directions since I have an odd power. Oops. My thing is just freaking out here. Okay, sorry. Since I have an odd power here, I should be going in 2 different directions than I am as on my ends. The rest of the points I need to the thing that's going to help me is if it's a multiple 0 or not. And that's how I'm going to know the rest of the direction. So this -1, 0, that's a multiple 0, has a multiplicity of 2, which is an even number. I know graph will change direction at that point. So I'm not going to continue through and go straight up. I'm going to change direction. I'm going to start going downwards. Eventually, I have to hit that y-intercept. And then to get to this point here, I'm going to have to go upwards. So not all of our graphs are going to look exactly the same for these problems, but it's important that you're going in the right direction. So that is what the graph of that polynomial is going to look like. Let's try another example. So example 2 here. I have y is equal to negative x plus 2 squared times x minus 5 squared. And if I break this down, it's going to be negative x plus 2 times x plus 2 times x minus 5 times x minus 5. So what I see, first things first, is end behavior. I want to talk about the end behavior first. I know when I multiply all of these together, standard form, I'm going to get y is equal to x to the 4th power plus a bunch of stuff. So x to the 4th power, why? X to the 4th power plus a bunch of stuff. But I'm only concerned about what that's going to be negative, sorry. Y is equal to negative x to the 4th power plus a bunch of stuff. So it's going to model y is equal to negative x to the 4th power, which I know the end behavior for that looks like this. Second thing I'm going to look for is the x-intercepts. So x-intercepts, I have, those are negative 2, 0, negative 2, 0, so that shows up twice. So multiplicity of 2, which means I'm going to change direction at that x-intercept. And then I have positive 5, 0, and positive 5, 0. So that shows up twice, which means I have a multiplicity of 2 again, which means the graph changes direction again at that point. So if I graph this thing, 2, 3, 4, 5, 2, 3, 4, 5. One more thing, y-intercept, important, you need that. So y-intercept is going to be, in this case, if I plug in 0, I'm going to have -1 times 2 times 2 times -5 times -5, which gives me a total of 4 times -5 is -20. -20 times -5 is 100. And then I multiply by that negative in front, so it's -100. So I'm going to be at -100. I'm just going to label that. Not going to draw 100 lines. And then I'm going to label the x-intercepts, which I know are 5, 0, and -1. -2, 0. And then I'm going to graph from there. So first things first, I'm going to graph the end behavior. So as I go to the left of this leftmost point, I'm going downwards, just like I am here. As I go from my right, the point farthest to the right, I am also going downwards. And then the rest of the direction in between is going to be decided based on the multiplicity. So I have a multiplicity of 2 for a -2, 0, which means I'm going to change direction. So I'm not going to keep going straight through. Not going to do that. I'm going to go the other way. So I was going upwards, now I'm going downwards, which makes sense because I have to hit that point, -100. Anyways, after I hit that point, at some point I'm going to turn around and I'm going to come back to this point here and I'm already finished. And that's what my graph is going to look like. All right, if I do example 3, end behavior to start, I know the end behavior is going to look, well, it's going to be y is equal to x cubed. I have 3 factors there multiplied together. So y equals x cubed, which I know looks like this. And then I'm going to look for my x-intercepts. So x-intercepts, and I have, my x-intercepts are -1, 0, 1, 0, and a -4, 0. And no multiplicities there, so I'll be going straight through all of these, not changing direction. And then my y-intercept is going to be when I plug in 0 for x always. That's 1 times -1 times 4 is what I'm going to get when I plug in 0 for these. And I get y is equal to -4. And then I'm going to 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Okay, that's not really even, that's fine. Y is equal to -4 right here. I have my x-intercepts I'm going to graph, -1, 0, 1, 0, and -4, 0. And then I'm going to use my end behavior to start. So from the leftmost point, as I go to the left from there, I should be going downwards, just like I am here in my end behavior. For my rightmost point, I should be going upwards, different directions, odd power, different directions I should be going in on each end. Then from there, actually, I'm gonna edit this because of the way I graphed. All right, and then from there, I should be going through all the points. So I was going upwards to get through, to get to this point here. So I should continue going upwards. Eventually, I'm going to have to go downwards to hit the other x-intercept here. And then I'm going to go straight through that, not change direction. I'm going to hit the y-intercept, and at some point, I'm going to turn around to get back to the last x-intercept. All right, example 4. The end behavior, end behavior is what I need first. The end behavior here is y is equal to, when I multiply all of this together, I have x to the 5th power. I'm going to have x to the 5th power, which looks like this, downwards and upwards. And then I'm talking about my x-intercepts. X-intercepts are, I gotta factor this thing more. So I have 3x times, this becomes x plus 2 times x minus 2. This becomes, x plus 3 times x minus 3. And I have all of these factors. First x-intercept is when 3x is equal to 0, which is 0. So I'm actually not going to write all the points. I'm just going to write 0 as one of my x-intercepts. To make this thing 0, I would have to plug in -2. To make this thing 0, I would need to plug in +2. To make this thing 0, I would need -3. And then for the last one, I would need +3. So those are all my x-intercepts. That's a lot of x-intercepts. And then for my y-intercept, I would have y is equal to, that's, the whole thing's going to be 0 because I have that factor of 3x. So it's just going to be 0 when I multiply. Because 0 times anything is 0. And then I'm going to graph these things. So 1, 2, 3, 4. 1, 2, 3, 4. And it doesn't matter what I put here and here. All right. My x-intercepts are 0, -2, +2. I have -3 and +3. And then my y-intercept is 0, 0, the same as that x-intercept. And then I know my end behavior is, as I go to the left, I'm going downwards. As I go to the right, I'm going upwards. In between, I should be going through all those points, straight through all of those points, not changing direction at them because there's no multiplicity. I don't see multiple zeros. So I'm going straight through here. Eventually I have to go down to get to the next intercept. I'm going to go straight through that. Eventually I have to turn around to get to the next x-intercept. I go straight through that, don't change direction, and eventually I have to go down to get to the next x-intercept, go straight through that, and go around eventually to get back to that other x-intercept that's left, and that's my graph.